Hello, my name is Robert James Nagy, and I'm a sophomore in the Environmental Studies program. With funds provided by the Reuben Zadigan Scholarship and help from classmates Rachel Wakefield and Sydney Becker, I investigated the effect soil temperature might have on polyester bee emergence. There are a large variety of polyester bee in the family Calididae. The focus of this project was Calides inequalis, a polyester bee native to Kansas and a majority of North America. They get their name due to a polyester lining that they secrete from a gland in their abdomen, called a Dufour's gland. Using their brush-like glossa, what we might think of as a tongue, C. inequalis coats the inside of their burrow. This cellophane lining gives it a waterproof sealing and has fungicide properties. Polyester bees nest in aggregations that range in size from a few dozen to several thousand. Typically emerging in late February to early March, C. inequalis is one of the first pollinators to emerge in the spring and plays an important role of pollinating early budding plants like redbuds, willow trees, and blueberries. It's clear that temperature plays an important role in insect development and spring emergence. As research on C. inequalis and other polyester bees continues, it's been observed that aggregations that receive more sun emerge 1 to 2 weeks earlier than aggregations located in areas that receive more shade. It was this that prompted my question. Does the spring emergence of Calides inequalis correlate with ground temperature? For this to appear true, aggregations that receive more sun would need to emerge earlier than those in shadier locations, and have warmer soils on average. To investigate this question, 3 aggregations on campus were selected with varying amounts of sun exposure, from full sun to mostly shade. Figure 3 was our full sun site, located on a south-facing slope. Figure 4 was the partial sun site, located in Marvin Grove. And our full shade site was the flower beds in front of Limley Hall, which received full shade for about half the day. Thermocron eye-button temperature loggers were used to record soil temperature. Programmed to record temperature in degrees Celsius every hour, loggers were placed in falcon tubes and wrapped in parafilm to keep waterproof. 2 loggers were buried at each aggregation, 11 to 12 inches, which is the average cell depth that C. inequalis is known to dig to. Loggers were buried on February 26th, and starting on March 1st, 1 or 2 individuals from the research team would travel to the sites and check for emerging C. inequalis each day. Figure 10 illustrates the average daily temperature high at each aggregation, with the red dots representing the first day's emergence was observed at each site. Here you can see at the Chancellor site that bees emerged on 3/11, while at the Marvin Grove aggregation, bees emerged on 3/10. 16 days later, after bees were first seen emerging at the Marvin Grove aggregation, bees were observed emerging at the Lindley aggregation. To the right, on figure 11, it illustrates the average daily temperatures between aggregations and the precipitation conditions throughout the month. Notice how similar the temperature trend is to the average daily high seen on figure 10. The first question is, why did it take a full 16 days longer for the bees at the Lindley aggregation to emerge? The average temperature throughout the month was 10.2 degrees Celsius at the Chancellor aggregation, 8.5 degrees Celsius at the Marvin Grove, and 8.3 degrees Celsius at the Lindley aggregation. We see that the Chancellor site consistently has a higher daily temperature, but Lindley and Marvin Groves stay rather consistent with each other, as you can see here. Except for this swarming trend right here. Early in March. We see that on March 10th, there's almost a 3-degree difference in temperature, possibly suggesting that more early accumulated heat led to emergence at Marvin Grove and not at Lindley. To better understand weather conditions that might have played a role in emergence, precipitation data provided by the National Weather Service was used. You can see precipitation conditions illustrated over the lines on Figure 11. From March 9th to the 18th, there was a period of cloudy and rainy conditions, seen here. Driving down temperatures and hindering insect activity. This transitioned to 3 days of clear skies and warmer conditions, represented by this sun right here. Rain followed for 6 more days, and then emergence was finally observed at Lindley on the 26th, right here. It's very possible that C. inequalis was ready to emerge days before the 26th, but could not due to the rain. Data suggests a possible link between sun exposure, ground temperature, and aggregation emergence, but further research is required to confirm or deny. Furthermore, precipitation also appears to play a significant role in emergence. In the future, investigating accumulated heat over the course of a year would be helpful to better understand how temperature impacts development. Likewise, continued temperature and emergence research should be continued at these 3 aggregations, as well as expanding this research to more aggregations at different latitude and longitudes. Myself and my group would like to extend our thanks to Dr. Smith and Dr. Hagen, whose contributions to the experimental design in providing tools and equipment were invaluable to the project. I appreciate your time. Thank you for attending my presentation.